It's Dr. Stephen Harrod again, and welcome. I'm coming to you from the Technical University of Denmark, and today I'm going to talk about the UIC 406 timetable compression method. Now, timetable compression and the UIC 406 method are all about trying to measure the utilization of your railway line. How busy is your railway line? And this is currently, the UIC 406 method is currently the dominant or most commonly used method today in high-density railway lines for measuring and quoting a statistic on how heavily the railway lines are used, or how much utilization, how much capacity is remaining as well. So let's get on to it. Let's go on and demonstrate how this method is applied. The 406 compression method is very simple, actually. We start with the string line, or the diagram of the train movements on the railway line. Here we have a basic string line. This is the track. This is the railway line up here with the signals on it. And then these are train paths here. These black lines are train paths. And each of these gray boxes is the occupation of this piece of track by this train as it passes through. Here's an occupation. Here's another occupation. Here's another occupation. And we have three trains, 1, 2, 3. These two trains are going in the same direction. They are going, I believe, let's say that these are going from left to right. And this train down here is going the opposite direction. That's why its line is sloped the other way. And it is going the opposite direction. I said these trains are going from left to right. Let's say that this is geography this way, and time, we could say time is going down on the scale here. So then this train is actually going from right to left, and it is going down this way in the time scale on the other direction of the track. So this is the way the timetable looks as we've graphically drawn it. As what we'd like to know is the utilization of this timetable. How aggressively is this piece of track being used? How much of this infrastructure is being used? So we do that simply by what's called compressing the timetable. So this is the compressed timetable. So what we're going to do is press these three trains close together so that they're almost touching, so that they're using just the minimum amount of time on this railway network. And what we have here on the right are two measures. The letter U, the capital letter U, is the original amount of time that these trains were occupying on the railway network. And this letter K, this smaller dimension, this is the amount of time that we are now using on this railway network. And we have compressed these, we have pushed them together so that we're using the minimum amount of time. And the ratio between these two, the ratio between K and U, is the utilization of this railway line. And clearly, the greater the difference, the more that we compress these trains together, then the more free space left over there is on the network, and then by definition, the less utilization that timetable actually had. On the other hand, if we come to this slide, come to this picture, and we can't press these trains together at all, and K and U are essentially the same numbers, then we would say that we already had a railway network that was at 100% utilization. So let's quickly try a little exercise for you folks at home. Here's an exercise. We have three trains, and we have the times that they enter and leave track blocks. We have three track blocks, A, B, and C. And we have the times that these trains take possession of the track block and then release the track block according to the signal system. So what you could do now, if you like, is pause this video for just a minute or so and draw this. draw the train diagram, draw the string line diagram for these trains as it is now with this timetable. And down here in step 1, here are the lengths of those track blocks. So draw that. I'll pause for a second, or you can stop the video now. And then now we're ready to go. So now let's go to the next slide. We'll start the video again. Here we go. So this is what your drawing should look like. This is what you should have drawn. This is the train occupations of the track blocks according to the timetable in the previous slide. And what we now want to do is we want to press these together. We want to compress this timetable because we now know that currently these occupy, let's see, starting at 9 a.m., going up to 15 o'clock over here. So we basically have 6 hours of occupation. We have 6 hours of track occupation with the timetable the way it is now. So we want to press these together and get a measurement on how much time they take when we've pressed the trains closely together. So I'm going to pause again. You can pause the video here. Try that. Take a moment and press those trains together and get a measurement. Okay, so now let's see the solution. So here is the solution. So we have pressed the trains together to compress them to get the minimum track occupation time. And so now you can see we're still starting at 9, but now the finish time is right about 13, 15, 20 some minutes after 1 o'clock. So the original time was about 365 minutes, 6 hours, and the new time is 270 minutes. So this timetable is at a 74% utilization of the railway. So now I want to demonstrate this in OpenTrack. So let's move on over to OpenTrack now. Okay, now one more thing before I actually go to the OpenTrack software. It's probably really faster and quicker if I explain a couple of key things with some graphics in a slide. So here's our OpenTrack model file. Here's the track. We have 10 stations. It's a straight piece of track, and it's just moved around on the screen to fit into the window, but actually all these track pieces are the same length. So that's 500 meters here, 500 meters here, and then 5 kilometers between 2 stations, and then it repeats. 500 meters, 500 meters, 5 kilometers. And we have signals. We have a home signal, and an exit signal, and an exit signal, and a station, and that's the same all the way through. So the trains, we've got 2 trains running on this track. These are a stopping train. In Danish, we call that a lokaltog, local train, and it's stopping at every station, like this. And then we have a fast train. In Danish, we call this the lyntog, the lightning train, and it is coming down here and only stopping at the 4th station and the 7th station, and then making its journey down like that. And I've already done this, and I won't do this in the video. I'll just give you the answer because I want to make this video short. We have already run the headway calculator, which is a tool in OpenTrack that allows us to determine the minimum spacing for 2 trains. And I have already calculated that if the lokaltog is following the lyntog, then they can depart a minimum of 179 seconds apart up at the starting station up here. And if it's the other way around, if the lyntog is following the lokaltog, it's much bigger. It's 759 seconds. So in any event, essentially 3 minutes up here and about 13 minutes down here, roughly. So 3 minutes and 13 minutes is really kind of our minimum feasible spacing for these trains, and we'll see later that we need to add even more time to that because that does not, the headway calculator does not fully take into account our station stop times and things like that. So that's just the minimum that we have as a starting point. Okay, so now you've got the starting, now you know where we're starting from, and now let's go on to the OpenTrack software. Okay, so here we are now. We are looking at the OpenTrack software, and we are now looking at the timetable window for OpenTrack. And here we are at the very beginning, and I have done very little work so far. And so I have the locale tow train in my timetable, and I am not showing you all of the processing steps that we have to go through to configure the routes and the paths and to create the courses and to that you will have to find that in another video. We're not going to do that today. That will take too long. So that has already been done. So we have already done that. We now have our locale tow in here, and it's going through its stations. And I've set up the dwell times. We have 30-second dwell, except for the major stations are a 60-second dwell. And this column for mean delay, we will not use that in today's video, so just ignore that. I'm going to leave that in there for another lesson, another time. So, and then we have our loon tow down here, starting and with its origin station, and then no stops until station 4, and then no stops until station 7, and then completing its trip at the last station. And these times, the dwell times, are kind of arbitrary. So if any of you out there are saying, well, I don't agree, I think the first station should have a much longer dwell time, well, you're probably right. But this is just an exercise, so that's not the point of the lesson today. So let's start out first. I've started out with the loon tow leaving first, actually, at noon. And then we have the locale tow leaving 3 minutes later, as we discussed, because that's the minimum headway that it can really have. And so I'm going to now edit this timetable to give these trains actual public timetable times. And I will do that and record it, but I will cut a significant part of that out when I actually edit the video. So here we go. I'm going to run it first to get some departure times in here, and then go through my timetable and edit it to create the final public timetable. Okay, I'm done. So I've got those basic times in for the very first timetable, and let's run this. And let's see the result. Let's take a scoot under here. And there's my result. There's my result. There are the trains on the timetable I've set, and you can see they're very close together up here, but they are not conflicting. There are no conflicts on there. And now I want to make a timetable, and I would like to make a timetable with some more trains. I'm going to say that this first hour is my working area, and I would like to fill it with departures from station 1 in this first hour. And let's see what we could do. Well, we know from the headway calculator that this definitely cannot, if I want to alternate these trains, I'm going to go loon tow, local tow, loon tow, local tow, loon tow, local tow. And that loon tow definitely cannot start any sooner than 13 minutes up here. And I'm going to tell you, I don't want to take the video time to demonstrate it, but I will promise you that actually what's going to happen is, because of these station stops that we've added in and the editing to the timetable that I've done, it in fact needs more, because the headway calculator can't compensate for all this extra time I've put in. So it really actually needs to be more. So at a minimum, the next loon toe can't depart. It's going to be 3 minutes plus 13 minutes, so that's 16 minutes. So really, at a minimum 16, and I'm going to tell you already because I've run this a bunch of times, that it actually needs to be a little bit more because there's still a little bit of a bump in here. So let's go ahead. Let's go ahead and do a 20-minute frequency. Let's do a 20-minute cycle time. So I want to have another loon toe 20 minutes later, and another locale toe 20 minutes after that. And let's do, we'll be able to fit 1, 2, well, let's just call it 2, really. Just 2 more into this timetable because the next 2 will jump over this 13 and land over here. And so let's just put 2 more in. So let's go to the timetable and let's do that. So I'm going to add 2 more locale toe, and they're going to be 20 minutes apart. I'm going to create 2 of them, and let's do that 20 minutes apart. Like that. And that looks good, and let's just do it. Let's run it. Okay, I'm going to say create, and there they are. There they are. They've been created. Show all the trains again and look at them. There's locale toe 1. We had that already before, leaving at 12:03. And now we have locale toe 2, number 3. It's the second locale toe, but they're odd numbered. So locale toe number 3 is the second train. So it's leaving at 12:23. And now we have locale toe number 5, which is the third train, leaving at 12:43 right there. So that is done. Now let's do the same thing with the loon toe. Make sure we've selected it. 20-minute cycle, 2 more trains, and create. And there they are. There they are. And let's show all. And there's loon toe leaving at noon. And there's my second loon toe. It says number 3, but it's the second. They're odd numbered. So it's loon toe 1, 3, and 5. So the second loon toe leaving at 12:20. And the third loon toe leaving at 12:40. So let's do that. So that's done. So let's save and let's run that and see what we get. And it's done. So there we go. There's our timetable now. There's our public timetable. And the trains are on a 20-minute cycle. And we're ready to take some notes. We're going to write some of this down. And then we're going to compress this timetable. We're going to compress it and do our compression calculation. But stop. Let's take a look here. Let's take a look. We could do it visually, looking at this diagram. But it's actually also pretty easy to read this from the timetable. What we want to know is this dimension down here. We want to know how much time. So this starts at noon, and it finishes when the last train is off the network here. Down here, we want to know this number down here, what this time is down here, and it's probably easier to read that off the timetable. So I want to know the arrival time of the last locale toe. So let's look at that. The last locale toe on my last simulation arrived, it exactly arrived at 13:26:43, but let's just go ahead and call it 13:27. So it arrived at 13:27. So we're going to write that down. Write that down, 13:27. Okay, now we want to compress this timetable. That means, by the way, so this was 1 hour and 27 minutes. This timetable is using 1 hour and 27 minutes. So now we want to compress this timetable. We want to compress this. So how are we going to do that? Well, there are a couple ways we could do that. We can do it visually up here. Remember, we could look at this and say, well, how much space do we have left here? We could kind of wing it a little bit. I'm going to tell you right now, if we zoom in here, if we zoom in really tight, I don't think there's any room here. This is done. This is compressed. This is as compressed as it's going to get. But we probably could compress a little bit on the distance between, and I'm zooming out here. We can probably compress it in the distance between the locale toe here and the loon toe here. Now the best way to do this is to delete these these other trains, I think, and then to manually put this back in. But before we delete all of that, let's do a couple of things. We want to do a little bit of an experiment. I need to figure out what this headway should be between these trains. There are a couple ways I could do that. I can eyeball it. I could come down. We could come down here and just look at this. We can look at these lines down here, and I could eyeball how much space I have down here. That's one way we could do it. I can make a good guess. But there's another way we could do this, and that is, first of all, let's get rid of these two trains first. Let's just delete those. So I'm going to go to courses, and I'm going to delete those. I'm going to delete that one. Yes. And the timetable. Yes. And I'm going to delete this one. Yes. And this. Yes, I do. And I'm going to delete, I want to delete this extra locale toe for now too. Let's get rid of that. So that locale toe is going away. Okay, that's good. That's good enough. And let's run it again to see what we're left with. Okay, now I want to manually move this loon toe in closer so that we see how close we can get. Now, how can I do that? Well, if I try to move this now, as you may have seen in some of my other lesson videos, you can readjust this whole timetable graphically by moving this. But if I move this, at the moment it's linked to this one, so I need to de-link those guys. So this train, loon toe 3, is linked to loon toe 1. I want to remove that link. So remove. And now when I do when I edit this, now when I make changes to this loon toe 3, it doesn't change the other train as well. So I'll go back to this timetable here. And I'm going to shift it, the whole thing. I'll grab these blue dots very carefully because I don't want to disturb the original pattern of the train. I just want to move it over evenly. And let's try that. And you can just see I'm really close. It's just getting close down here, and then there was a little bit of a violation. This round circle down here is a violation, and you know, you could go a little crazy trying to get this to be exactly perfect, but it's pretty close if we're no conflict, no conflict, no conflict, and we only get just a little bit of a conflict way down here. I could tinker with this a little bit more, and now we want to go the other direction just a couple of seconds, maybe like 30 seconds, 20 seconds. Let's try that. Yeah, that's pretty good. I mean, I don't really see a conflict down here. Let's zoom in. No, there's nothing there. It was literally just a matter of tens of seconds. There's no conflict. Let me back out again. We're good. We're good right there. That's really good. So what have I learned? Well, I can go back to the timetable and find out exactly what the headway should be between these trains. So let's go back and look at the timetable. And what have I done? Let's take a look. So according to the timetable, 18 minutes and 10 seconds is the headway now between two loon toes. So if there's 18 minutes and 10 seconds between two loon toes, then I can also go 18, so that's a cycle, that's this repeating of the cycle. So if there's 18 minutes and 10 seconds from here to here, then I can add another local toe over here, also exactly 18 minutes and 10 seconds over here. So let's remember that, 18 minutes and 10 seconds, so let's do that. 18 minutes and 10 seconds. Let's clean things up a little bit here. Let's go to courses. We're going to delete this guy. No, we can leave it. I don't have to do that. Let's just leave that alone. I don't have to do anything. Let's leave that alone. Now we need to add our extra trains. So I need to add one more loon toe, and it needs to be 18 minutes and 10 seconds more. Just going to create one more. Yes, this should work. And I need to do that for the locale toe. I need two more locale toes, and they're 18 minutes and 10 seconds. I need two more of those. And I think I'm done. Let's run that. Oops, wrong way. Yeah, I'm done. There we go. Looks pretty good. Looks pretty good. I'm about as tight as I can get. So let's take a look at this. So I can get my number. So I'm going to get my number off of the timetable here. So the last locale toe came in at 13 minutes and 23. So an hour 23. An hour 23. So we didn't get a lot of compression out of that, right? And why? Because this timetable was already pretty tight. It was already pretty tight when we started. It was already at this, that eyeballed 20 minutes was already pretty tight right there. So let's do the math. I'm going to leave OpenTrack and let's go to the board. And so here we are with the final result. Here's a picture of our final compressed train schedule right here. And here's the data that we collected. The original timetable was 87 minutes. And we got that because the last arriving train arrived at 13:27 and the first departing train was at 12 noon. So that was 87 minutes right there. And then this timetable here is 83 minutes because its last train is arriving a few minutes sooner. And we take the ratio of those two, 83 divided by 87, and we can say that this public timetable, the original timetable I started with, was a 95% utilization, which is really high. That is not realistic in a real-world situation. That is, in the real world, we would probably want that number to be down around 80 or 75%. But that's the number we have based on this toy problem, based on this little example problem I've done here. And one of the reasons it's so tight, you look at this, notice there's so much white space in here. There's a lot of white space in here. So even though the network calculation says we're using almost all of the network, 95%, it's mostly because of these non-standard train speeds. We have one train running many stops and one train running express, and this white space in between them is wasted. We can't use it. Even though the calculation says we're operating at a very high utilization, that's not the same thing as efficiency, and you can see we're not really very efficient. All this white space is unused track time. So that's something to think about. That's something for another lesson at a future time. The question of how we make more efficient use of the railway network. Well, that wraps up our little short lesson on UIC 406 compression and a demonstration in OpenTrack. So until next time, this is Dr. Stephen Herod from the Technical University of Denmark, and I look forward to speaking to you again. Bye-bye.